Right, we're back. Sorry about the stream keep cutting out. I don't know. I don't think my iPad likes streaming too much. I've lowered the quality and lowered I've lowered FPS, half the FPS and lowered the quality to 720. So hopefully it won't cut out anymore. I'll start this question again. So we'll go from scratch so you can see what my thoughts were. But hopefully that won't be happening again. Let's see if this actually is working. Yep, there we are. So sorry about that, guys. We will try it again. So yeah, when we're doing vectors questions, what we always want to do is basically we're going to have some point that we don't know. We don't know where it is. And we're going to try and find it in two different directions. So here, we're told that C is twice OA. So if we have the line O to A, we can just double that, whack it on this end. That's going to be C up there. And M is the midpoint of A to B. So it's going to be that point down there. And as we draw this line and cut it through, it goes through the bottom line, A to B, down there. So as it goes through that line at the bottom, it creates some new point N. And we don't know exactly where that one is. We know everything else is, like this is 1 and this is 1, so they're equal lengths. But we don't know exactly where the N is. But we do have two ways to get there. We can do that red journey by going like we do the rest of it as well, do this little bit of it. We can do that red journey, or we can go along the bottom with the blue journey. So two different ways that we can get there from O to N. So we want to find the two different ways to go from O to N, once in the red way and once in the blue way. How do we do the red way? Well, we have to go from O to C and then from C to N. So O to C plus C to N. What's O to C? 2O to A. C to N, well, we don't know where N is, but I do know where M is. So what I can say is, well, it's the same as doing that journey, but then just so much more of it. So it's like X times as long as C to M. Well, X might be, say, like 1.4, and then it means that this journey was, there's an extra 40% on to do that little bit at the end. So once we've done that, let's just keep going. We know where C to M is, but how do we actually get there? Well, we can go this way. So it's going to be 2, or the OA as well, it's just 2A, yeah? That's just 2A, that's the kind of definition of it. But then the second bit, C to M, like I say, we can go to A and then to M. So that's going to be C to A plus A to M. C to A we know. That's going to be minus A. The A to M is a half of A to B. And A to B is going to be minus A plus B. I think that would have been, well, we would have had this already, but we can work it out as we go. So what we're going to do then, yeah, this is going to be a half of that journey. So half of A to B is B minus A. That looks good. Let's just expand some brackets here. So I've got 2A still at the front, plus what's going to be inside this bracket? Well, there's a half of a B. That's it, times an X. So I'm going to half X, lots of B. How many A's? Well, I've got minus 1 there, minus another half, so minus 3 on 2. So minus 3x on 2, lots of A. And I'm going to factorize this for the A's and the B's. So I've got 2 minus 3x on 2, lots of A, plus an x on 2, lots of B. So you always want it in terms of your A's and B's. So that's good. That's the red way, and we've got there in terms of A's and B's. Let's just shrink that up, put it to the side a little bit. The blue way then, what we need to do is just think, oh, well, it's so much of O to B, isn't it? Yeah. So one way often it's just a very simple version. This is going to be so much of O to B, which is so much of B. And now then these two versions are equal because they're both referring to journeys from the origin to N. So no matter which way you did get there, they must be the same thing. So what we can say is that the 2 minus 3x on 2 is equal to 0, and the y is equal to x on 2. So looking at like the A's and the B's. That top row, what does it tell us? X is going to be 4/3. And therefore, when we half that, what do we get? Y is going to be 2/3. So now we've figured everything out. What the question's asking us. What is C to M? Well, we did that in here somewhere, didn't we? It's this thing. It's the inside of this bracket. So what we do have is C to M. It's going to be, yeah, inside the bracket. What did we have? It was a half of B minus 3 halves of A, wouldn't it? Must be a half of 3B minus A. Show that that's true. Yep, we've shown it's true. It's the same thing, yeah. It's exactly the same idea. Maybe just write it down to make sure. But therefore, O to n implies that, oh no, that's just that, yeah. It is just that, yeah, ignore me. It is just that thing. Last bit then, prove that this is 2 to 1. Well, O to n, n to b. What we have, we knew that y was 2/3 of this journey. So what we have is that is 2/3. This is going to be 1/3, therefore, on the other side. So that is in the ratio of 2 to 3. So this just implies by itself that O to n is equal to 2/3 of O to b. And therefore we have, well, that's going to imply that the n to b will be the other third. What's that going to tell us is that the ratio between them, this one must be twice as much as that one, yeah? So O to n to n to b is 1, 2, 2. 2 to 1, sorry, 2 to 1, other way around. The one on the left is twice as big as the one on the right. Lovely, that all looks good to me. Any other questions you guys got? Whack them in the comments. If not, like I said, I'll just carry on doing random ones from here. But I'd rather do questions that like you're stuck on or little bits that you're not sure of. Actually, I'll show you something that is quite useful that you might not have seen. So when you do by parts, the general goal of it is you want to end up in a situation where the u is differentiating away, yeah? So say you had x cubed, you then make x squared, then x, then a number, and then it's just gone. But what happens if we have something like this? If we have e to the x times sine x, because the sine x is going to differentiate all the way around, e to the x is going to differentiate all the way around. So they're never going to go away. So I call them cyclic differentials. And in this case, we're just going to start as normal. So the actual formula, uv dash is equal to uv minus u dash v. So if we make our u sine x, so our u dash is going to be cos of x, v dash then, e to the x, and v will be e to the x as well. As we get our integration, like the second part of it, we're going to have e to the x sine x take away the integral of e to the x cos x. This is very similar, isn't it? Like what we put out here is very similar to what we started with. So let's just do the same thing. U can be cos. U dash therefore will be minus sine. V dash e to the x. And v will also be e to the x. So doing this again, e to the x sine x, take away the uv. So take away e to the x cos x. And now we need to take away the negative of these bits. So we've got 1, 2, 3 negatives makes a positive. No, 3 negatives makes a negative. Integral of e to the x sine x. This thing is what we're looking for. So if we just like call this thing I, everything we've done down here, this is equal to I. This is equal to I. And this thing is I. So we can add that one over and have 2 i's and then half it. So 2i will be e to the x. I'll factorize as well. Sine x minus cos x. And then, yeah, divide by 2. So the integral should be e to the x on 2. Sine of x minus cos of x. So this is like, yeah, cyclic differentials. I don't know if that's a correct name for them. It's always what I've called them. Cyclic differentials. So where e to the x stays at e to the x, they go around the little circle, don't they? Sine to cos to minus sine to minus cos. And with that, yeah, if they pop up next to each other, the by parts formula will still work. But the next row, if you did like just by parts again, like say you didn't do this version, but you did by parts again, you would undo. You'd have a minus e to the x sine x, and the next one would have a positive e to the x cos x, and you'd end up after 4 goes of it back where you started, which you don't want to do in the exam. That's going to be very demoralizing. So as you get the same thing appear again, just rearrange for that. If you get sine and cos, yeah, if you get sine and cos popping up, then like sine times cos, do you mean in the top, like sine and cos there, there's nothing else? Just make it sine 2x, and then integrate sine 2x like a half of sine of cos 2x, or minus a half. So anything else you want to look at? Maybe stats. Oh, stats. Yeah, maybe. We'll see. We'll see about stats. I'll decide how I if I can be bothered. But it probably is a yes. It probably is a yes. I will do it at some point. But it's just like, oh, stats. And also, yeah, fuck the large data set. Fuck that thing. So I'm not doing the large data set. We're just going to skip those questions. We'll talk about it, but yeah, we're not going to do them. Circle theorems. Circle theorems. I don't know if you're going to have circle theorems come up. We can do like something about circles, like coordinate geometry, but I won't do circle theorems, like GCSE version of it. But we'll see if you've got any like random circle questions in here that are appearing. Oh yeah, what's this thing? Show the area of that thing. Okay. So what do we need to do? Always on these ones, just go and make it. Go and draw it into like some weird shape, yeah? So how can we just connect these lines up? Let's do that. And that. And these are going to be sectors, aren't they, yeah? If we were to continue out, this is a radius. We could draw like another radius and another radius. And we should see that all of these are going to be like the same as each other. Whether this is actually a hexagon is a different question. Like it might not be a hexagon. But I think we're going to have this case where like all of these bits, you can draw that triangle. And then like this blue section, do you know what I mean, is the same as this one. I think looking at it, like that looks like it fits. You just design that to be exactly the right number, do you know what I mean, to make it work. I think that should be fine. I don't see any issue with that. So what number is that going to be? Well, this is an equilateral triangle, yeah? So we know that it should be 60 degrees. So it's going to be pi on 3. So how do we work out that little blue section? It's going to be the area of a segment. So to do that, one area of a sector, r squared theta on 2. Take away the area of the triangle, which is r squared 2 sine theta. So factorising that, r squared on 2 at the front, theta minus sine theta. And we know that it's going to be pi on 3, yeah? What is sine of pi on 3? It's not 0.01, is it? If we put things in radians, what do we get? Root 3 on 2. So this is going to be r squared on 2, lots of pi on 3, take away root 3 on 2. That's for the blue bit. That's blue. Let's actually colour that blue, maybe. And once we've got that blue bit, we can obviously see there's 2 of them in there, yeah? There's this bit up here as well. So I'm going to work out then this sector. Well, what is that sector? I'm assuming it's going to be like, we can fit that. Is that going to be a radius? I hope it is going to be. I'm assuming it is, and then we'll see if it pops out. Like the root 3's appeared. That's the root 3's there. That's probably good. We've got a pi as well. So hopefully that's the right way around of thinking about it. If it's not, we'll see if it's wrong, and then we'll try and fix it. But I'm going to assume like this is a radius on the top. There's probably some way you can show it, but I'm assuming that is that, and then there's going to be pi on 3 there. Because this all looks like it fits very nicely, doesn't it? If it was a hexagon exactly. So I'm going to assume it is, and then if it's not, if it's broken, then we'll fix it. But if it's not broken, we'll stroll through and hope it's right. So how do we work out the area of that one? Well, it's the circle again, isn't it? So it's not the circle, the triangle. So not the sector even, sorry. So we're going to have the area of the sector. So let's usually label stuff, yeah. Sector area will be r squared theta on 2. So it's going to be r squared times by a half of the angle. I'm assuming then pi on 3 again. So it's going to be pi on 6. Does that look good? Yeah, it's starting to look, bits look nice, don't they? Bits look nice when things appear. So what do we have? That's the big bit there. That's the pizza slice. And we want that pizza slice, but without 2 of the orange slices. So we want 1 pizza slice. So pi, r squared on 6, lots of pi. Take away 2 of these pizza slices. So take away 2 of that, we'll just get rid of the half. R squared pi on 3 minus root 3 on 2. And then let's expand everything out. Well, not expand, maybe we'll take away some r squared. What we left with, I've got pi on 6 minus pi on 3 plus root 3 on 2. What's this give me? Well, it's a 6, take away a third, so it's a minus a 6. So r squared of, we'll put the root 3 on 2 first. Minus pi on 6. And then let's take a 6 out the front. What do we get? R squared on 6. I need to triple the first bit and just leave the last bit alone. Is that correct? Yeah, lovely. So sometimes if you're not sure exactly what it is, just assume like it looks like it fits, doesn't it? Yeah, looks like it fits. The numbers that it gives me is good. Like it gives me a 6, it gives me that stuff. So like bits are matching. So just because you're not 100% sure, sometimes it's like if you have no other ideas, do you know what I mean? Try something, see if it's going to work. And oh look, it did give you exactly what you wanted in the show that questions. So not too bad. Lovely. Right. What's going to go on here then next? Let's see what else we've got. Anything else? But like I say, any other questions you've got, whack them in the comments. If not, we'll try and do some bits that you guys maybe like we haven't done so far today. Do you know what I mean? So maybe we'll do this one with the integration. Or if there's any other topics you guys have, whack them in the comments. This is a few bits done it because this has got, you can see a tangent, and we've got the area between the curve and the tangent. So what do we need to do? We have this curve, we want to differentiate it, has an x coordinate of 4, find the tangent, and find the area between them. Okay, so dy dx, what we're going to get, 3, it's not a bigger 3, is it? 3. This is minus 4x to the half. So what we're going to get, times it by a half, we'll have minus 2, x to the minus 1 or 2. We want to find it, this has 0.4, so if we evaluate that when x is equal to 4, what we're going to get, well, 3, well, that's over 2, yeah, that's a half. So it's 3 take 1, it's going to be 2. So that is our gradient. We still want the y coordinate as well. So y is going to be 12, take away 4 times 2 is 8, plus a 2, should be 6. So we've got y minus 6 equals 2 lots of x minus 4. And y therefore should be 2x, that'd be minus 8 plus a 6 minus 2. Lovely. 6 marks. 6 marks. I don't think you'll get 6 marks for that tomorrow. So from here then, what else do we need to do? We want to find... No, we don't need that point actually. No, we don't need that point. We can just do the integration in it. No, we do need that point. It's going to be slightly different. That point should be nice and easy though. Make this be y is 0. So that happens when x is 1, which is good. Let's not do a circle though. And we're going to split this up then. Where the bit to the right hand side we want to do like underneath there. Actually, no, let's think it a little bit differently. Where we'll just do the normal integral. What that will find us, like if we do the integral between the curve and the tangent, it will find the area including this little triangle, and then we can just take it away. So we'll call this like the little blue triangle. It's going to be like that little section of it. So our integral will find everything, including that blue triangle, and then we take it away. So we're going to integrate the curve, take the tangent, between 0 and a, which was 4. What was the curve? It's going to be 3x minus 4 and then the square root of x plus the 2. Take away this thing. So take away 2x and plus a 2. Let's collect some bits first. What we're going to have, still 4 and 0 up there. We've got 3x, take 2x is x. We've still got this square root part, so minus 4 root x. And then the numbers, we got plus 4. So doing this, what do we get? X goes to x squared, divide by that 2. The power goes to x to the 3 on 2. So you're going to have 4 times 2/3. So if everyone's sure on doing that, yeah, just raise the power, then flip the power, whack it there. It's always correct. And then it's going to be 4x over there. We won't have a plus c because we've got some limits. 0 and this stuff, nice and straightforward. All going to be just zeros, yeah. Let's sort this out. I need 2/3 of 4, so that is 8/3. And then let's plug in some 4s. 4 squared, 16. Half of that is 8. 4 squared root of 2, cube it's 8. 64 on 3. Plus a 16. What number is that going to be? Let's find out. 8 plus 16 minus 64 on 3. I get 8/3. That's very nice. Does it make sense? Does it make sense? It's 2 and 2/3. This had a value of 4, and was it 6? Yeah, 6. So this has coordinates 4, 6. So if you think about the whole kind of area here, this would go for it minus 2 as well. That's minus 2. So this big box, as we fill everything in, it's 4 wide, 8 tall. So 32. We're less than 32, definitely. And we should be looking at it a lot less, yeah? So having a number of like 3, 2 and 2/3, that seems sensible. It seems correct. From here then, what's the area of this triangle? Well, it's got a width of 1, height of 2. So area of 2 times 1 is 2. half of that is 1. So answer should be the area, therefore, 8/3, take away 1 is 5/3. Again, I might make some number errors, but it does, the method should be good. Methods that we use to work stuff out should be correct. Do some modeling stuff. Yeah, we can find some modeling stuff if you want. Let's see what modeling bits we've got in here. So we did that one. Have we got anything that's about modeling that's not rates of change? I think we did earlier on, didn't we? If not, I'll go and find something else. Anything we can see? We'll scroll through proper. It's this thing, wasn't it? Yeah, maybe this thing. Yeah, we're modeling some design here on something. So figure 3 shows a design because there are 2 rectangles measured by x and y. So and the angle in there is half a radius. So the area is 50. The area of this thing is 50. Okay, so we have got all of that bit filled in. So lovely. Let's write down then a formula for this area. This is always what you need to have. There's like some formula that you're going to use to work stuff out. So we have area is a number. We want to get some like expression for it too. What do we get? We have 2 rectangles that are y times x. So that's 2xy. And then we have this sector where it's got half a radius. Half of the radians is a half. So normally for sector area, we're going to have r squared theta on 2. R squared in this case is x, so it's x squared on 2. But the radius there is halved, so it's going to actually be a quarter, not on 2. This looks good. From here then, we know that is 50. 50, not 40. And we want to work out something about the perimeter. So let's write down some formula for the perimeter as well. We've got an x. Let's actually think about it. Yeah, we've got an x there, an x there. So 2 x's. I've got y, 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 and y. 4 y's. And then I have like the arc. So it's r times theta. So r is x, theta is a half, so it's x on 2. Just collecting those bits up. 2 and a half is going to be 5 on 2. So 5x on 2 plus 4y. So now we have these 2 different bits. One for perimeter, one for area. One of them we know a value. So what we're going to do is take the one that we know the value for and rearrange it to eliminate one of the variables. Look down here, there is no y. So we want to somehow get rid of this. How do we do that? Rearrange this for y. So taking the top one, if I actually kind of just put this on the other side for a sec. Taking the top one, we'll subtract the x squared on 4. So 2xy will be 50 minus x squared on 4. And then we're going to divide by 2x. So y should be 25 on x. Take away x on 8. Am I doing that right? Yeah. And look at some of these bits. Like, that's good. We have a 4y doing. You can kind of tell before you get there, are you correct? Look a little bit ahead. Do things match? Yes. Wonderful. Then let's keep going. If they don't, stop. Something's gone wrong somewhere. As soon as you realise you're wrong, there's no point keeping going. Because you're just going to be more wrong. So when you know you're wrong, stop, have a look at something else, see if you can fix it. Right, so let's plug this thing into this thing. So that tells us that P will still be the 5x on 2, but now we need to quadruple all of these bits. So we're going to add on 100 on x, and then take away 4 lots of an eighth is going to be a half. So take away x on 2. So 2.5, take away half, 2x plus 100 on x. Not too bad, yeah? So area, perimeter, they told you a value for the area. If you're unsure, just go and circle the bits you have. Area, perimeter. What nouns have they told you? Figure 3. So you've got 2 rectangles. And mathsy nouns, do you mean circular sector, radius, angle, area, perimeter. You've got numbers, 50. So we have area is 50. Area equals 50. That's what it means in terms of maths. So you always have one thing here, use that to get a relationship between your x and y, rearrange that, replace one of the variables to sub it into the other thing you're thinking of. Find when it's a minimum, so we'll differentiate it. It's going to rewrite that as 100 x to the minus 1. So dp, dx will be 2. Take away 100 on x squared. So times them by the negative 1, dropping that power from minus 1 to minus 2. So we want to solve that equal to 0. So we can have that basically equal to each other, yeah. if I put that x up there, put that 2 down there, x squared is 50. X is going to be the root of 50, which is something 5 root 2. And show it is a minimum. So we need the second derivative, dp squared, not d squared p, dx squared. Again, this is minus 100 to the x to the minus 2. My 2, that goes away, that doesn't change. This thing will be 200 on x cubed. And what we can say is that that is just always positive if you put a positive thing in there. So it's going to be bigger than 0 for all x, which are bigger than 0. So therefore, it is a minimum. So at no point do you need to plug it in. It's obvious that's going to be positive if you put something positive in there. So save yourself the 30 seconds on the calculator, putting it in there, and then like you might put it in wrong. That's an extra mistake you can make. That thing is clearly positive if x is positive. So it's a minimum. Find the minimum value. So we had it occurs at 5 root 2. We want to take that and plug it back into the original thing for the perimeter. So perimeter evaluated when x is 512. X equals 5. Oh, sorry, 5 root 2, not 512. We 2 times that. So it's going to be 10 root 2 plus 100 on that. So 100 on 5 is 20. 20 on root 2. If we do those bits, we've still got the 10 at the front. 10 root 2. Times here, top and bottom by root 2. On the bottom, it's 2. With the 20 makes a 10. That's another 10 root 2. So all together, I think 20 root 2. Hopefully that's good. Again, method's always right. I might get some numbers just slightly wrong along the way. Yeah, hope that's all good. Hope that all makes sense. If you give me 2 seconds, I'm just going to run to the toilet and then I'll be back, yeah. Right, I'm back. So, yeah, any other questions we've got? What are we thinking of doing? Yeah, hopefully these model ones are not too bad. You always have the 3. Again, look at what variables you have. Area, perimeter. It's got to be something to do with that. You want to forget a thing for perimeter. So somewhere you have a value for the area. And you want to plug that in and then use that to get some relationship between x and y. Replace the y then using that thing, sub it in, and expand that until you get what you want. Hopefully that's all good. Yeah, any other questions, leave them in the chat. If not, we'll just keep going through this. Yeah, anything else, give me a shout. So what have we got in here then? Center stuff. We've done some circles already. Yeah, let's do some trig maybe. Let's get a bit of a harder trig one than that. Let's look at the end of the thing and work our way backwards. Where the answers start. Yeah, we'll look at this one. So what do we do for trig? We want to make sure the inside matches this. What do we mean by that? So right now we have x, we don't have that. So let's add pi on 4 everywhere. So this is the same. Pi on 4 is less than or equal to x plus pi on 4, which is less than 2 1/4 is 9/4. So 9 pi on 4. And this then becomes the range of just the normal function where we want to find it. So if we're to draw tan out, what do we have? We're only going to draw it between those 2 points. So it's going to come up, like in general it does this. Where would that be? That's 90 degrees. So that's 90 to 70. I know it's radians, but sometimes it's easier to draw it first, isn't it, without the radians. And then put the radians in. We go up again, do that stuff, and this is 540. So what are they in terms of radians? Pi on 2, 3 pi on 2, and 5 pi on 2. So that's too far. Oh, we've drawn too much of it. We need to cut it off from like this point, halfway in between these lines, basically. So from that point and to that point. That's our cutoff. So let's actually rub out those little bits. Precision. So yeah, these bits don't exist in our graph. And what we want, oh, other way around, sorry, these bits. What we want to happen is that we hit 3. So we need to go through and see where does the line 3 hit our curve. Either it's going to be up there, or it's going to go down and like hit the right hand side here, do you mean? Or like the left hand side there. Where that happens, we're not too sure, but we'll get that when we put in the solutions. What I would generally do is do that. And then like one of them will be a yes, and one will be a no. So how do we do this? We're going to do the inverse tan of 3. At that point, what number do we get? Inverse tan of 3, 1.249. So 1.25. I will again look at what is that in terms of degrees, just so I have an idea in my head about where it is. It's 71. This is 45, is where we cut off, it is 45. So our green line is up. Yeah, this is 45, this is 71. So we know we hit that point, but we don't hit on this side. So where are our solutions? We're going to have that the x plus the pi on 4, the thing inside our brackets, is 1.25 and 1.25 plus pi. So x is going to be those two things, 1.25, take away pi on 4, and 1.25 plus now 3/4 of pi on 4. That looks good. Yeah, that looks good to me. So always kind of matching, take your domain and rearrange it into the thing that's inside the tan there. Always making it match up like that. Lovely. Let's look at part B, see what's going on. Find in terms of pi, the values of y in this interval for which this is going to be true. Okay, so when you've got like sine and tan in there, we need to think about what is tan. Well, it's sine over cos, yeah? This is sine y over cos y. Bring this all to one side. We'll have 2 lots of sine y. Well, let's take the sine y out as well. We'll have sine y, lots of 2 minus 1 on cos, which is sec, equals 0. So effectively we need sine y equals 0, or sec is equal to 2, so cos is equal to half. That should be implied, should be a comma. So yeah, both of these are going to be fine. What was our interval? 0 to 2 pi. So nothing freaky going on there. Are we allowed to be 0? Yes. We're allowed to be 2 pi? No. So what does this left one tell us? Y is 0 or pi. Cos of a half, if we do inverse cos of a half, what do we get? Is it 60? Yeah, 60. So what's that? 2 pi on, no, pi on 3. So again, drawing it out, what are we going to have? Cos starts on the top, goes down, goes back up again. We want it to be a half. So we have uno y dos. If that side was 60 degrees, i.e. pi on 3, let's do a different colour. This side was pi on 3, yeah, from the end. So is this side. They're symmetrical, all the way through, symmetrical. So for that second one, we're going to have that y is equal to pi on 3 and 2 pi. Take away that. So 6 pi on 3, take away 2 pi, 1 pi on 3, gives us 5 pi on 3. And that should be then all the answers that we get for that one. Lovely jubbly. Yeah, a third of pi and 5/3 of pi. Yeah, spot on. Well done. My student sent me a text about one past paper he's done. Let's see if we've had any stuff that needs to be done. Let's see. I'm going to ask him on stream. Can I mark it on there? I'll double check that he wants to do that. If not, I will just do some other questions. But it might be good to see some like what goes wrong in some of them. Do you know what I mean? So we can have a look and see what's happening. But for the time being, we'll have a look at some things here. Some circles or geometric sequence. Blah 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 blah. Penguin draws a series of circles, each with a touch in the previous one. So the center's line a horizontal straight line. radii of the circles for the geometric sequence. First 1 mil, second 1.5. Okay, so what we have there, A then, the first one is 1, isn't it? And R is going to be 1.5, so 3 on 2. Find the rate of the 4 circle to be drawn. Well, okay, we need to just do, well, it's going to be AR to the AR cubed, yeah? So it's just R cubed in this place. So 27 on 8. That's good to me. Show that when 8 circles have been drawn, W is equal to this. The width of the design is shown as this. Okay, so that is the sum of them, yeah? Because each one is going to be the radius times by 2. So we want to add up all the radii, i.e. do the sum of 8. When we have these values, A is 1 and R is that. So it's going to be A, lots of R minus 1 minus R to the n over 1 minus R. Let's plug this in, see what we get. 1 minus 1.5 to the power of 8 over 1 minus 1.5. I get a number of 6305 on 128. That looks good. And then from this one, you think that's going to be for all the radii, but W is equal to 2 times that. So 2 times that thing, it's going to be 2 times all of this. So it's 2 times all of that. So it should be 6305 on 64. What number is that? It is 98.5-ish, which is what they wanted. Lovely. Find the total area of the design when 10 circles have been drawn. So here, I think we need to think a little bit more sneaky. We have the first one is going to be like pi r squared. Yeah, the first one's going to be a in it for the radius, so we're going to have pi times a squared. But the next one is going to be pi times ar all squared. And then the next one after that is going to be pi times ar cubed. No, not like that. Yeah, hold on. Let's start again. Let's think about our sequence. We have a, then we have ar, then we have ar squared, then ar cubed. So these bits are going to be the radius. So we have pi times all of those squared. So a squared, pi a squared r squared, pi a squared r to the 4, pi a squared r to the 6. So the original starting value is going to be a squared now. That's still 1. We take a pi out as well, yeah? So pi a squared at the front. And then it is 1 plus r squared plus r to the 4 plus r to the 6 plus blah, blah, blah. This is good. So our common ratio of this sequence is just going to be r squared. So we want to have the sum of the first 10. So it's going to be pi a squared at the front still. And then 10 of these things. The first time is a. So we're going to have 1 minus r to the n. R is now r squared. 9 on 4. So 9 on 4 all squared over 1 minus r. So let's see what that's given us. The a as well. The a was 1, wasn't it? So it's just pi at the front there. What have we got though? Fraction 1 minus 2.25 squared over 1 minus 2.25. I get 13 on 4. So I think that's 13 pi on 4. Again, maybe numbers are wrong. Methods should still be right there in the way that we're thinking about it. Yeah, hopefully that seems not too bad. So if you're unsure on these, like draw out sequences, do and see what's going on. I was trying to do it in my head, but if you just draw them out, it's easy to see. Okay, pi times that thing squared, and it square all the bits times by pi should be the area of a circle. Right, some 5-marker vector questions. Yeah, I'll see what other ones pop up. Let's have a look at doing some of those bits. Let's see, A-level maths, vectors, questions. What's going to pop up? Vector revision. Questions by topic. Let's do second year, obviously. Do you mean ones like this, where you're just doing vector things? Or like, okay, well, there's one option there, let's do some other ones. Get out of there. Let's go to the actual ones from the past papers. Yeah, what sort of vectors are you meaning? You mean the ones where you have to find like lambda and mu and stuff, or ones who just need to like show it's a parallelogram and stuff? Like we did that question a second ago. Got ones here. What sort of vector one? 3D vectors. Ooh, okay. Stuff like this, yeah. And this is only one mark actually. Well, we'll do it quick, but we'll find some other ones as well. Yeah, what about these?